Hello, everyone. In this section, we will introduce the small signal equivalent circuit of bipolar junction transistors, or BJTs. After introducing the basic idea of a BJT amplifier, let us analyze this amplifier again, starting from the DC operating point. At a DC bias of VBE, the collector current IC equals IS times the exponential of VBE over VT. Here, VBE over VT is the term inside the exponential function. The emitter current IE equals IC divided by alpha, and the base current IB equals IC divided by beta. Finally, the output voltage VO equals VC equals VCE, which equals VCC minus IC times RC. From the total signal point of view, the signal contains both a DC part and a small signal AC part. The total output voltage is VO, or VCE, equal to VCC minus the total collector current IC times RC. The total collector current IC equals IS times the exponential of the total input voltage VBE over VT. Since the total input voltage is the DC bias VBE plus the small signal voltage VBE, the exponential term can be separated into two parts. Therefore, IC equals IS times exponential of DC VE over VT multiplied by exponential of small signal VBE over VT. The first part is the DC collector current IC, so IC equals IC times exponential of VBE over VT. When the small signal voltage VBE is much smaller than the thermal voltage VT, the exponential of VBE over VT can be approximated as 1 plus VBE over VT. In other words, the ratio VBE over VT is the small quantity inside the exponential function. Substituting this approximation back into the equation, the total collector current IC becomes IC plus IC over VT times VBE. This shows that IC can be separated into a DC component IC and an AC component that depends on the small signal voltage VBE. The AC collector current, called small signal IC, is IC over VT multiplied by VBE. The small signal collector current IC equals IC over VT times VBE. We define the factor IC over VT as the transconductance GM. It can also be obtained by taking the derivative of the total collector current IC with respect to the total base emitter voltage VBE at the DC operating point. In other words, before we can calculate the small signal current, we must first know the DC collector current IC. To summarize, the total collector current IC is the DC collector current IC plus the small signal collector current IC. The small signal collector current equals GM times VBE. The transconductance GM of a BJT is the derivative of collector current with respect to the total BE junction voltage VBE. After separating the collector current into DC and AC parts, let us look at the base current. Since the total base current IB equals the total collector current IC divided by beta, IB can also be separated into the DC base current IB and the small signal base current IB. Therefore, small signal IB equals small signal IC divided by beta, which also equals GM times VBE divided by beta. From this relationship, the small signal base emitter voltage VBE equals the small signal base current IB multiplied by beta over GM. We define beta over GM as R pi. This is also equal to beta times VT over IC, or equivalently VT over IB. Therefore, from the base current point of view, the BE junction can be modeled as an equivalent resistance R pi carrying the small signal base current IB. Next, let us discuss the emitter current. Similar to the base current, the total emitter current IE equals the total collector current IC divided by alpha. Since IC has both a DC component and an AC component, IE can also be separated into IE and small signal IE. The small signal emitter current IE equals small signal IC divided by alpha, or GM times VBE divided by alpha. From this, the small signal base emitter voltage VBE equals the small signal emitter current IE multiplied by alpha over GM. We define alpha over GM as RE. This is also equal to alpha times VT over IC, or VT over IE. Therefore, from the emitter current point of view, the BE junction can be modeled as an equivalent resistance RE carrying the small signal emitter current IE. Earlier, using the base current, we obtained VBE equals IB times R pi. Using the emitter current, we also obtained VBE equals IE times RE. Since both expressions describe the same VBE, IB times R pi equals IE times RE. Because IE over IB equals 1 plus beta, R pi equals 1 plus beta times RE. The same BE junction voltage can therefore be described using either the base current and R pi or the emitter current and RE. Which form is more convenient depends on whether the circuit analysis is based on IB or IE. As shown in the figure, if the signal is applied at the base and the emitter is grounded, the input resistance seen looking into the base is R in equals input voltage over input current. This is VBE over IB, which equals R pi. Therefore, from the base terminal, the BE junction can be simplified as an equivalent resistance R pi. Similarly, if the signal is applied at the emitter and the base is grounded, the input resistance seen looking into the emitter is R in equals input voltage over input current. This becomes VEB divided by negative IE, which is equivalent to VBE over IE, and therefore equals RE. So from the emitter terminal, the BE junction can be simplified as an equivalent resistance RE. Now let us return to the basic BJT amplifier and analyze the output voltage. The total output voltage VO equals VCE, which equals VCC minus the total collector current IC times RC. Since IC equals IC plus small signal IC, the output voltage becomes VCC minus IC times RC minus small signal IC times RC. The first two terms form the DC output voltage, and the negative IC times RC term is the small signal output voltage VO or VCE. Therefore, the small signal VCE is negative IC times RC, which is also negative GM times VB times RC. The voltage gain of this amplifier is the small signal output voltage VO divided by the small signal input voltage VI. In this circuit, that is VCE over VBE equal to negative GM times RC or negative IC over VT times RC. This is the same result we derived earlier. After these derivations, we can see that every terminal voltage and current in a BJT amplifier can be written as a DC value plus a small signal AC value. For example, the total base emitter voltage VBE is the DC bias VBE plus the small signal VBE. The total base current IB is IB plus IB, and the same idea applies to the other terminals. Therefore, circuit analysis can be separated into DC analysis and AC small signal analysis. Since DC analysis was covered earlier, we focus here on the AC part. For AC analysis, we isolate the small signal equivalent circuit. In this circuit, an ideal DC voltage source becomes a short circuit, so the VCC terminal becomes small signal ground. This is because small signal resistance is defined as a voltage change divided by a current change. For an ideal voltage source, the voltage change is zero no matter how much the current changes, so it behaves like a short circuit. For an ideal current source, the current change is zero no matter how much the voltage changes, so it behaves like an open circuit. For a BJT, there are two common small signal equivalent circuit models. We first introduced the pi model. This model is built directly from the small signal electrical relationships of the BJT. From the small signal characteristics, we have IC equals GM times VBE. This means the collector current is controlled by the base emitter small signal voltage. Therefore, the collector side can be represented by a dependent current source controlled by VBE, as shown in the equivalent circuit. Also, VBE equals IB times R pi, and this voltage is often called V pi. Therefore, the base current IB equals VBE divided by R pi. This means the base side of the BJT can be represented by the resistance R pi with IB flowing through it. The remaining emitter current IE is the sum of IB and IC. If the early effect is also considered, the collector current is affected by VCE as well. As VCE increases, the collector current increases approximately linearly. As introduced earlier, this effect can be modeled by placing an output resistance RO between the collector and emitter. In the small signal model, the collector current becomes GM times VBE plus VCE over RO. The value of RO is the early voltage VA divided by the DC collector current IC. Besides the pi model, a BJT can also be represented by the T model. Starting again from the collector current equation, IC equals GM times VBE, and it also equals alpha times IE. This means the collector current can be obtained from the emitter current. Since IE equals VBE divided by RE, or equivalently VBE equals IE times RE, the BE junction voltage can be represented by an emitter side resistance RE carrying the emitter current IE. This is the T model. If the early effect is included in the T model, the same output resistance RO is placed between the collector and emitter to represent the additional current contribution caused by VCE. Now let us compare the pi model and the T model. Their main difference is how the BE junction resistance is represented. If we describe the junction using the base current IB, the resistance is R pi and VBE equals IB times R pi. If we describe it using the emitter current IE, the resistance is RE and VBE equals IE times RE. The pi model is convenient when the base or emitter is directly grounded because VBE or IB can be found directly. The T model is usually more convenient when the emitter has an external resistor because we can first find IE and then convert it to IC. After introducing the basic BJT amplifier and its small signal models, let us work through an example. The circuit has DC bias supplies VCC and VBB, a small signal input voltage VI connected through the base resistor, and the small signal output voltage VO taken at the collector. We first perform DC analysis. In DC analysis, the AC signal source is set to 0, giving the DC equivalent circuit shown in the figure. As in the previous DC BJT circuit analysis, we start from the base to emitter path. Since the emitter is directly grounded, VE equals 0 volts. Using the approximation VBE equals 0.7 volts, the base voltage VB is 0.7 volts. The base current IB is then VBB minus VB divided by RB. Numerically, this is 3 volts minus 0.7 volts divided by 100 kiloohms, giving 0.023 milliamps. Using IC equals beta times IB, the collector current is 100 times 0.023 milliamps, which equals 2.3 milliamps. Then the collector voltage is VCC minus IC times RC, or 10 volts minus 2.3 milliamps times 3 kiloohms, which equals 3.1 volts. Since VCE is 3.1 volts, greater than 0.3 volts, the BJT is operating in active mode. Finally, IE equals IB plus IC, which is 2.323 milliamps. After DC analysis, we can calculate the small signal model parameters. The transconductance GM equals IC over VT, so it is 2.3 milliamps divided by 0.025 volts, which gives 92 milliamps per volt. The resistance R pi equals beta over GM, or 100 divided by 92 milliamps per volt, giving 1.09 kiloohms. The emitter resistance RE equals alpha over GM, which is approximately 0.99 divided by 92 milliamps per volt, or about 10.8 ohms. Next, we perform AC analysis. All DC voltage sources are set to 0, and any ideal DC current sources would become open circuits. Only the AC signal source remains. Therefore, the circuit seen by the small signal is different from the DC circuit. Then we replace the BJT with the pi model, obtaining the small signal equivalent circuit shown below. Now we analyze the small signal equivalent circuit. Starting from the base to emitter path, the base current IB is the input voltage VI divided by the series combination of RB and R pi. The small signal voltage VBE can also be obtained by voltage division. VBE equals R pi over RB plus R pi multiplied by VI. After VBE is found, the collector current IC equals GM times VBE. The output voltage is VO equals negative IC times RC, or negative GM times VBE times RC. Therefore, the intrinsic voltage gain AV equals VO over VBE, which is negative GM times RC. The global gain GV equals VO over VI, which includes the input voltage division factor R pi over RB plus R pi. Substituting the values from DC analysis, the voltage gain AV equals negative 92 milliamps per volt times 3 kiloohms, which gives negative 276 volts per volt. The global gain GV equals the input division factor, 1.09 kiloohms over 100 kiloohms plus 1.09 kiloohms multiplied by negative 276, which gives about negative 3 volts per volt. For faster small signal analysis, we do not always need to draw the full BJT equivalent circuit. The key point is that the base emitter PN junction behaves like an equivalent resistance in small signal analysis. If the resistance is described using the base current IB, it is R pi in the pi model. If it is described using the emitter current IE, it is RE in the T model. In this example, since VE equals 0 volts, it is more convenient to use R pi and solve for IB. Therefore, we can immediately see that VBE is obtained by voltage division between RB and R pi. So VBE equals R pi over RB plus R pi multiplied by VI. Then using IC equals GM times VBE, the output voltage is VO equals negative IC times RC, or negative GM times VBE times RC. From this, both the voltage gain and the global gain can be obtained directly. Next, let us consider another example. This is a PNP-BJT circuit. The input signal VI is applied at the emitter, and the output signal VO is taken at the collector. There are coupling capacitors connected in series with both VI and VO. As usual, we start with DC analysis. For DC analysis, the impedance of a capacitor is infinite, so the capacitor is treated as an open circuit. Its purpose is to block DC and prevent the AC signal path from disturbing the DC bias point. The DC analysis still starts from the base to emitter path. Since VB equals 0 volts and VEB is approximately 0.7 volts, the emitter voltage VE is 0.7 volts. Therefore, IE equals VE minus VE divided by RE, which is 10 volts minus 0.7 volts divided by 10 kiloohms, giving 0.93 milliamps. Using IC equals alpha times IE, IC is about 0.92 milliamps. Then VC equals negative VCC plus IC times RC, or negative 10 volts plus 0.92 milliamps times 5 kiloohms, giving negative 5.4 volts. Since VEC equals 0.7 volts minus negative 5.4 volts, which is 6.1 volts and greater than 0.3 volts, the BJT is in active mode. Finally, IB equals IE minus IC, about 0.01 milliamps. After the DC operating point is found, we calculate the small signal parameters. The transconductance GM equals IC over VT, which is 0.92 milliamps divided by 0.025 volts, giving 36.8 milliamps per volt. The emitter resistance RE equals alpha over GM, so it is about 0.99 divided by 36.8 milliamps per volt, giving 27 ohms. Now we move to AC analysis. All DC sources are set to 0, leaving only the AC signal source. For small signal analysis, the impedance of the coupling capacitor is 1 over J omega C. Since C is assumed to approach infinity, this impedance approaches 0, so the capacitor can be treated as a short circuit. In other words, a sufficiently large coupling capacitor has almost no effect on the midband small signal analysis. Its effect becomes important only at low frequencies, which will be discussed later in frequency response. Next, we replace the BJT with the T model, giving the small signal equivalent circuit shown on the right. In this equivalent circuit, the base is grounded, so we can directly compute the emitter current. The small signal emitter current IE equals VBE divided by RE, which here is VI divided by RE. The collector current can be obtained from IC equals GM times VEB, or equivalently from IC equals alpha times IE. Since RE equals alpha over GM, both approaches give IC equals GM times VI. Therefore, the output voltage is VO equals IC times RC, or GM times VI times RC. The voltage gain VO over VI is therefore GM times RC equal to 36.8 milliamps per volt times 5 kiloohms, or 184 volts per volt. This concludes the introduction to the small signal equivalent circuit of bipolar junction transistors. Please look forward to the next lecture. See you next time. Bye-bye.